A comet from beyond our solar system is doing something near the largest planet in our cosmic neighbourhood that makes absolutely no sense, and one of the world's most credible scientists thinks it might be dispatching probes to spy on Jupiter. This isn't science fiction. This is the type of scenario that could be happening, that telescopes would need to track around the world, and the implications are staggering enough that they could fundamentally change how we see our place in the universe. This isn't speculation pulled from internet forums. The object designated 3I Atlas by astronomers has been tracked by 230 observatories worldwide. NASA's Jet Propulsion Laboratory calculated its trajectory. The numbers were published by Avi Loeb, Harvard's former astronomy department chair. And what those numbers show is so statistically improbable, one chance in 26,000, that it's forcing serious scientists to ask questions they never thought they'd have to ask. The object is called 3I Atlas, an interstellar visitor that travelled through the dark void between stars for potentially millions of years before entering our solar system. We've only known about a handful of these interstellar objects, and each one raises more questions than answers. But 3I Atlas is different. As it moves through space on its trajectory past Jupiter, it's exhibiting behaviour that has astronomers scratching their heads and checking their instruments. The brightness changes don't match what we expect. The timing of these changes correlates with its approach to Jupiter in ways that feel less like coincidence and more like intentional action. And Avi Loeb, the former chair of Harvard's astronomy department, has put forward a theory that sounds like it belongs in a movie, but is grounded in careful scientific reasoning. What if this isn't just a comet? What if it's artificial? What if it's dropping something near Jupiter? I know how that sounds. Trust me, I know. But stay with me here, because over the next several minutes, we're going to walk through exactly why serious scientists are asking these questions, what evidence exists that challenges our comfortable assumptions about comets and interstellar objects, and why Jupiter specifically. Jupiter might be the most logical place in our solar system for any intelligence to conduct reconnaissance. We'll examine the data, confront the skepticism, and explore what it would mean if we're witnessing something that textbooks will struggle to explain. This isn't about jumping to conclusions. This is about following evidence wherever it leads, even when it takes us somewhere uncomfortable. Because here's what we know for certain. 3I Atlas is not behaving like a normal comet. Its trajectory brought it from interstellar space into our solar system, and as it approaches Jupiter, something is changing. Something is happening that astronomers are still trying to explain with conventional theories, and those explanations are showing cracks. The timing is suspicious, the patterns are unusual, and the possibility that we're seeing something unprecedented isn't coming from internet conspiracy theorists. It's coming from scientists with credentials that put them at the very top of their field. Think about what it takes for a Harvard astronomer to publicly suggest that an object might be artificial. Think about the career risk, the peer ridicule, the scrutiny that comes with making such a claim. Avi Loeb isn't doing this for attention. He's doing it because the data demands that we at least consider possibilities we've been trained to dismiss. He's doing it because ignoring uncomfortable hypotheses isn't science, it's dogma. And he's doing it because we're living in a unique moment in human history where we finally have the technology to detect things we couldn't see before, which means we need to be willing to see them, even when they challenge everything we thought we knew. So what exactly is 3I Atlas doing near Jupiter? What patterns are emerging that don't fit the standard comet model? Why would any intelligence care about Jupiter in the first place? And perhaps most importantly, how would we even know if we were looking at technology rather than natural phenomena? These are the questions that matter. These are the questions that could define this decade in astronomy. And these are the questions we're going to explore together, following the evidence step by step, building a case the way any good investigation should be built, with facts, with context, and with intellectual honesty about what we do and don't know. You're about to see why some of the smartest people studying our universe think we might be witnessing something that future generations will look back on as the moment everything changed. You're about to understand why Jupiter isn't just another planet in this story, it's potentially the key to understanding why 3I Atlas came here at all. And you're about to confront a possibility that most people haven't seriously considered, that our solar system might be under observation, that reconnaissance might be happening right now, and that we're finally advanced enough to notice. But before we dive into the details, I need you to do something. If this topic matters to you, if you're the kind of person who wants to follow evidence rather than comfortable assumptions, hit that like button right now. Let me know in the comments which planet you think would be most strategically important if you were studying our solar system from the outside. Would it be Jupiter, Earth, or something else entirely? And subscribe, because this is exactly the kind of story that's going to develop over the coming months and years, and you'll want to be part of the conversation as new data emerges. This isn't entertainment. This is real astronomy happening in real time, and we're all watching history unfold together. Now let's start with what makes 3I Atlas so different from every other comet we've studied, because until you understand just how strange this object is, you can't fully appreciate why scientists are considering explanations that would have seemed ridiculous just a few years ago. When astronomers first track a comet, they know what to expect. Comets are predictable. They're chunks of ice, rock, and frozen gases that have been orbiting through space for billions of years, and when they get close to the Sun, they heat up, start out gassing, develop those beautiful tails we see in photographs, and behave according to well-understood physics. We've studied thousands of comets. We know their rhythms. We know their patterns. We know how they brighten as they approach the Sun and how they fade as they move away. Comets are one of the most reliable, predictable phenomena in all of astronomy. That's what makes 3I Atlas so deeply unsettling, because it's not following the rules. The first thing that caught attention was the brightness. Comets brighten as they approach the Sun due to increased outgassing the ice on their surface vaporizes, creating the characteristic coma and tail. This process is gradual, predictable, and directly correlated with solar distance. But 3I Atlas showed brightness variations that didn't match this pattern. After perihelion, observers documented multiple jets erupting from the object, unusual outflow patterns that created brightness changes. These weren't smooth, gradual changes. They were more erratic, more sudden, more like something was changing on the object itself rather than just responding to external heat. Now, before you think this alone proves anything extraordinary, it doesn't. Comets can fragment. They can have irregular rotation. They can have pockets of volatile materials that release suddenly. All of these things can cause brightness variations. But here's where it gets interesting. The timing of these variations seem to correlate with the object's position relative to Jupiter. As 3I Atlas moved through space on its trajectory, the anomalous behavior became more pronounced as it approached the Jovian system. That correlation is what made astronomers start paying closer attention. Because coincidences in astronomy are rarely just coincidences, they're usually clues pointing toward underlying mechanisms we don't yet understand. What's remarkable is that 3I Atlas showed measurable non-gravitational acceleration. Some force was pushing it, and that push changed its trajectory by exactly the amount needed to bring it straight toward Jupiter's gravitational boundary. Not close, not near, exactly there. Not impacting Jupiter, not getting captured by Jupiter's gravity, but passing through that region of space where Jupiter's gravitational influence is strongest. For an object that travelled for potentially millions of years through the void between stars, arriving at our solar system and then taking a path that brings it specifically into proximity with the largest planet we have, that's a trajectory that makes you wonder. Here's how precise this is. Jupiter has a gravitational boundary the exact distance where its pull dominates. NASA calculated that 3I Atlas will pass right at that boundary edge. Not roughly close, not in the general area, at the exact boundary. The odds of that happening by chance? 1 in 26,000, where Jupiter's gravity dominates everything, where any passing object has to account for a planet more massive than all the others combined. Nothing definitive enough to declare it wasn't a comet, but enough to make researchers double-check their instruments and wonder if there was something about interstellar comets that we simply didn't understand yet, because we'd only seen a couple of them. Here's what makes this frustrating from a scientific perspective. We're dealing with an object that's far away, moving fast, and only visible for a limited window of time. Making this more mysterious, 3I Atlas reached perihelion while hidden behind the Sun from Earth's perspective. We couldn't observe it during the critical window when that measured non-gravitational acceleration occurred. We don't know if it simply adjusted course naturally through outgassing, or if something else happened during that observation gap. Every measurement has margins of error, so when something doesn't quite fit expectations, you can't immediately tell whether it's because the object is genuinely unusual or because your data isn't perfect. This is the reality of astronomy. You're trying to understand objects millions of kilometers away using light that's traveled across space, and you have to make educated guesses about what you're seeing. But educated guesses are still guesses, and that's where pattern recognition becomes crucial. When astronomers look at 3i Atlas, they're not just looking at one anomalous data point. They're looking at a constellation of small oddities that individually might mean nothing, but collectively paint a picture of something that doesn't quite match what we expect. The brightness variations that don't perfectly correlate with solar distance, the trajectory that brought it near Jupiter, the spectral signatures that mostly fit but have those nagging little discrepancies, the timing of behavioural changes, none of these things alone would be enough to make you question whether this is just a comet. But together they create a pattern that demands explanation. And that's exactly what the astronomical community has been trying to do: explain this pattern using known physics, known comet behaviour, and known natural processes. Most scientists believe they can explain 3i Atlas without invoking anything extraordinary. They point to the fact that interstellar comets might simply be different from solar system comets because they formed in different stellar environments, around different stars under different conditions. They suggest that what we're seeing is simply our first real look at how comets from other stellar systems behave, and we shouldn't be surprised that they're not identical to the comets we've studied for centuries in our own solar system. That's a reasonable position. That's the position most astronomers hold. But it's also a position that has gaps. It's a position that requires you to accept that every oddity, every anomaly, every unexpected behaviour is just part of natural variation that we haven't seen before because our sample size of interstellar objects is so small. And maybe that's true. Maybe we're just dealing with a comet that formed around a star dozens or hundreds of light years away, and everything unusual about it is simply because it's a product of a different stellar neighbourhood. But there's another possibility, one that most scientists are reluctant to voice publicly because of how it sounds, how it invites ridicule, how it challenges the fundamental assumption that everything we see in space has a natural explanation. What if 3i Atlas isn't just a comet? What if the reason it doesn't quite fit our models is because it was never meant to fit those models? What if the trajectory toward Jupiter wasn't random chance but intentional navigation? What if the brightness changes aren't outgassing but something else entirely? Power fluctuations, course corrections, or activities we can't even imagine because we've never seen technology operating in deep space? That possibility is what brings us to Avi Loeb, because he's one of the few scientists with the credentials and the courage to say out loud what others might privately wonder. He's the scientist who looked at another interstellar object, Oumuamua, and said this might not be natural. He's the researcher who built his career on rigorous mainstream science, but who refuses to dismiss possibilities just because they're uncomfortable. And when he looks at 3i Atlas, he sees the same kinds of patterns that made him question Oumuamua patterns that are easier to explain with intelligence than with ice and rock. Which means we need to talk about exactly who Avi Loeb is, why his opinion carries weight even when it's controversial, and why dismissing him as a fringe theorist is intellectually dishonest, because understanding the messenger is crucial to evaluating the message, and this particular messenger has a track record that demands we at least listen to what he's saying. Avi Loeb isn't some YouTube personality with a telescope making wild claims for clicks. He's not a retired engineer with too much time on his hands and a conspiracy theory blog. He's not a fringe figure operating on the margins of academia. Avi Loeb is the former chair of the astronomy department at Harvard University. He's published hundreds of peer-reviewed papers. He's advised government agencies on scientific matters. He's mentored dozens of PhD students who've gone on to successful careers in astrophysics. His contributions to cosmology, black hole physics, and the early universe have been cited thousands of times by other researchers. In the world of professional astronomy, you don't get much more mainstream than Avi Loeb, which is exactly what makes his willingness to consider extraterrestrial explanations for unusual astronomical objects so significant. Let's go back to Oumuamua for a moment, because that's where Loeb's public journey into controversial territory began. In 2017, astronomers detected an object moving through our solar system that was clearly interstellar in origin. Its speed and trajectory made that undeniable. Oumuamua, as it was named, was the first confirmed interstellar object ever detected. Initially, everyone assumed it was either a comet or an asteroid from another star system. But as observations continued, Oumuamua did something strange. It accelerated as it moved away from the Sun, but without showing any signs of outgassing that would normally cause such acceleration in a comet. It was pushed by something, but not by the mechanism that pushes comets. Various natural explanations were proposed. Maybe it was outgassing material we couldn't detect. Maybe it had an unusual shape that caused solar radiation pressure to push it more than expected. Maybe it was made of solid hydrogen ice that outgassed invisibly. But each of these explanations required adding special assumptions to make the data fit. They required making Oumuamua unusual in very specific ways that were each individually unlikely. And Avi Loeb looked at this situation and asked a question that most scientists avoided. What if we're overcomplicating this because we refuse to consider the simplest explanation? His suggestion was straightforward. What if Oumuamua was artificial? What if it was a light sail, a thin, flat object designed to be pushed by radiation pressure, either from stars or from some propulsion system we couldn't detect? That would explain the acceleration without outgassing. That would explain the unusual shape that observation suggested. That would explain why it didn't behave like any natural object we'd seen before. It was, in Loeb's assessment, a more parsimonious explanation than inventing new types of comets made of materials we'd never seen, and that happened to outgas in ways we couldn't detect. The response from the astronomical community was swift and harsh. Loeb was accused of seeking attention. He was criticized for promoting ideas without sufficient evidence. He was told that extraordinary claims require extraordinary evidence, and that proposing alien technology based on one unusual object was irresponsible. The pushback was intense, and it continues to this day. But here's what's important. The criticisms weren't primarily about the logic of his argument. They were about the conclusion. The structure of his reasoning was sound. He was applying Occam's razor, preferring the explanation that required fewer ad hoc assumptions. The problem was that his conclusion pointed toward intelligence, and that's a conclusion the scientific community is deeply uncomfortable reaching. Why is that? Why is suggesting an object might be artificial so controversial, when we're perfectly comfortable suggesting all sorts of unusual natural phenomena we've never observed before? The answer is partly historical and partly psychological. Science has been burned before by jumping to extraordinary conclusions that turned out to be wrong. Pulsars were briefly thought to be alien signals before we understood they were rotating neutron stars. Various radio signals have been attributed to possible alien origins before natural explanations were found. Science has learned to be conservative, to assume natural explanations until absolutely forced to consider alternatives. That conservatism has served science well. It prevents us from seeing aliens in every shadow. But conservatism can also become dogma, when you're so committed to natural explanations that you'll invent increasingly complicated natural mechanisms rather than consider the possibility of technology. You're no longer being conservative, you're being closed-minded. And that's Loeb's fundamental critique of how modern astronomy approaches the question of technosignatures. We've become so afraid of being wrong about aliens that we've made it almost impossible to ever be right about aliens, even if they're actually there. We've created an intellectual environment where suggesting an object might be artificial is career suicide, which means even when objects show characteristics consistent with technology, we'll default to natural explanations no matter how contrived they have to be. Loeb's argument isn't that every weird object is aliens. It's that we should evaluate each object on its merits, consider all possibilities including artificial ones, and let the data guide us rather than our preconceptions. He's arguing for intellectual honesty and openness to evidence rather than predetermined conclusions. And he's willing to be wrong. He's explicitly said that if better natural explanations emerge for Oumuamua or 3i Atlas, he'll happily accept them. What he won't accept is dismissing the artificial hypothesis without even seriously considering it, which is what he believes most of his colleagues are doing. This brings us back to 3i Atlas. When Loeb looks at this object, he's not immediately jumping to aliens. He's looking at the patterns, comparing them to what we'd expect from natural objects, and asking whether those patterns might be more consistent with technology than with ice and rock. He's asking whether the trajectory makes sense for reconnaissance. He's asking whether the timing of behavior changes correlates with strategic locations like Jupiter. He's asking whether we're seeing something that's easier to explain if we assume intelligence rather than assuming nature. And here's the crucial part. Loeb's methodology is actually more rigorous than his critics often acknowledge. He's not making unfalsifiable claims. He's proposing testable hypotheses. If 3i Atlas is artificial and deploying something near Jupiter, that should be detectable with better observations. If it's natural, continued study should reveal the natural mechanisms causing its unusual behavior. This is how science is supposed to work. You propose competing hypotheses and then gather data to distinguish between them. The problem is that one of those hypotheses has been declared off limits by scientific culture, which means we're not actually doing science anymore. We're doing scientific materialism, which is a philosophical position masquerading as empiricism. Loeb has also built his argument on precedent and probability. He points out that we now know there are billions of potentially habitable planets in our galaxy. We know that life emerged on Earth relatively quickly after conditions became favourable. We know that technology, once it emerges, can spread and persist for long periods. Given these facts, the probability that we're alone in the galaxy is actually quite low according to most serious assessments. And if we're not alone, if technology exists elsewhere, then statistically some of that technology should be detectable in our astronomical observations. The question isn't whether it's out there, the question is whether we're willing to recognise it when we see it. This is why Loeb can't be ignored, even when his conclusions are uncomfortable. Because he's not operating from the fringe, he's operating from the centre of astronomy, using the same tools and methods as everyone else, just without the artificial constraint that says technology is an impermissible answer. He's following evidence where it leads rather than where it's comfortable to go. And in the case of 3i Atlas, where it leads is toward a possibility that sounds like science fiction, but might just be science fact, that this object is doing something intentional near Jupiter, and that something involves deploying smaller objects or instruments into that region of space. So what exactly is this deployment theory? What would it look like if a civilization from another star sent reconnaissance technology into our solar system? Why would they care about Jupiter specifically? And how would such technology even work across the vast distances of interstellar space? These are the questions we need to explore next, because understanding the theory means understanding what we should be looking for, what evidence would support it, and what evidence would refute it, and that's the only way to have an honest conversation about whether 3i Atlas might be more than just a comet. Imagine you're a civilization that's mastered interstellar travel, or at least mastered sending instruments across the void between stars. You've identified a stellar system that might be interesting maybe, because it has planets in the habitable zone, maybe because spectroscopic analysis suggests complex chemistry, maybe because you've detected electromagnetic signatures suggesting technology. You want to learn more, but even travelling at a significant fraction of light speed, sending a crewed mission would take decades or centuries. So instead you send probes, small, efficient, long-lasting instruments that can surveil, record and transmit data back across the light years. But here's the problem, stopping is hard. If you accelerate a probe to the speeds necessary for interstellar travel, slowing it down again requires enormous energy. You either need fuel, which adds mass and makes the journey harder, or you need some kind of braking mechanism like a magnetic sail or light sail operating in reverse, which adds complexity and risk. A more efficient approach would be to have your probe pass through the target system at high speed, but deploy smaller sub-probes that can slow down and take up observation positions while the parent craft continues on its trajectory. Think of it like a plane dropping paratroopers. The plane doesn't land, it just releases its payload while maintaining speed. This is the model Avi Loeb is suggesting might explain what we're seeing with 3i Atlas. The main object is the carrier, coming from interstellar space on a trajectory that takes it through our solar system. As it approaches Jupiter, it deploys smaller instruments, probes, sensors, relay devices, whatever you want to call them, that can establish orbits or positions near Jupiter and begin whatever observation or data collection mission they were sent to accomplish. The parent object then continues on its way, either to exit our solar system or to visit other points of interest, while the deployed instruments remain behind, doing their work over months, years, or even longer. Why would this approach make sense? Because Jupiter is arguably the most scientifically valuable location in our solar system for reconnaissance aside from Earth itself. Jupiter's massive gravitational field shapes the architecture of our entire solar system. Its influence determines which asteroids and comets can reach the inner planets. Its radio emissions can be detected from enormous distances, providing a navigation beacon. Its complex system of moons includes worlds like Europa and Ganymede that might harbour subsurface oceans, and potentially even life. And Jupiter's position in the solar system gives you a vantage point from which you can observe the inner planets, including Earth, without being too close, avoiding whatever detection capabilities might exist on those worlds. Let's think about this from an engineering perspective. What would a deployed probe need to do? It would need to separate from the parent craft, which means some kind of release mechanism or ejection system. It would need to slow down relative to the parent craft, which means propulsion capability, even if minimal. It would need power, which means either solar panels, radioisotope generators, or some technology we don't have. It would need sensors to collect data. It would need some way to store or transmit that data, either back to the parent craft, back to the origin civilization, or to some relay system. And it would need to survive the harsh environment of space, including radiation, micrometeorite impacts, and temperature extremes. All of this is technically feasible with technology not far beyond what we currently have. We've built interplanetary probes, we've built systems that last decades in space, we've built instruments that can survive Jupiter's intense radiation environment, we've sent multiple missions to Jupiter and its moons. The idea that another civilization with even moderately more advanced technology than ours could build small, durable probes and send them on interstellar journeys isn't science fiction, it's engineering extrapolation. We can imagine it because we can almost do it ourselves. Now, what would such a deployment look like from our observational perspective? This is critical because if we're going to evaluate whether 3i Atlas might be doing this, we need to know what we'd expect to see. First, we'd potentially observe sudden changes in the parent object's brightness or behavior as it releases the probes. Depending on the mechanism used, there might be flashes, puffs of expelled material, or changes in rotation. These changes would be brief and might be subtle, especially if the probes are small compared to the parent object. But they would be changes that don't fit the normal comet outgassing model, because they wouldn't correlate with solar heating, they'd correlate with position, specifically with approach to the deployment location. Second, if the probes are reflective or emit any kind of radiation, we might detect them as separate objects after deployment. But this is where things get difficult, because we're talking about potentially small objects at vast distances. Our telescopes can detect large objects in the outer solar system, but something the size of a car or a bus at Jupiter's distance might be below our detection threshold, unless it's specifically designed to be bright, or unless we know exactly where to look. And if whoever built these probes didn't want them easily detected, they could minimize reflectivity and emissions, making them essentially invisible to our current observation capabilities. Third, we might detect unusual electromagnetic signatures. If the probes are communicating with the parent craft with each other, or with some distant home base, they're transmitting signals. Those signals would need to be powerful enough to cross interstellar distances if they're going back to the origin civilization. Or they'd need to be collected and relayed by the parent craft or some other system. If we happen to be in the beam path of such transmissions, we detect them. That's essentially what SETI programs are looking for. But space is vast and transmission beams can be narrow, so the absence of detected signals doesn't mean there are no signals, just that we might not be in the right position to receive them. The timing question is important here. If 3i Atlas started showing unusual behavior specifically as it approached Jupiter, that timing is suspicious in exactly the right way. It suggests that whatever is happening isn't just random outgassing or fragmentation that could happen anywhere along the trajectory. It's something happening at a specific location, at a specific time, as if it were planned. Natural processes don't care about Jupiter's location. They care about solar distance, or about internal stresses that build up gradually. But if you're executing a deployment plan, you care very much about location. You want to release your probes at the optimal point in your trajectory, where they can most efficiently reach their intended positions. Critics of this theory will immediately point out that we have natural explanations for brightness changes and trajectory oddities. They'll say that invoking technology is premature when we haven't exhausted natural possibilities. And they have a point, we should always prefer natural explanations when they adequately explain observations. But here's the tension. How many times do natural explanations need to be stretched? How many ad hoc assumptions do we need to add? How many unlikely coincidences do we need to accept before we admit that maybe the reason natural explanations keep falling short is because we're looking at something that isn't natural? This isn't about proving 3i Atlas is artificial. We can't prove that with current data. But it's about acknowledging that artificial is a possibility worth investigating seriously, rather than dismissing reflexively. It's about recognizing that if we were looking at human-made technology exhibiting the same behaviors, we wouldn't hesitate to identify it as technology. The only reason we hesitate with 3i Atlas is because it's coming from interstellar space, and we've never confirmed that technology from another civilization exists. But the absence of confirmation isn't the same as the absence of existence. We've only been seriously looking for a few decades. The universe has been producing civilizations potentially for billions of years. The odds that we'd find technology in our very first surveys are low, but the odds that technology exists somewhere are high. Think about what humanity would do if we could send probes to another star system. What would we target? We'd look for planets that might have life. We'd study stellar systems with interesting configurations. We'd investigate phenomena we can't observe from our own location. And we'd probably send probes that could deploy sub-probes, maximizing our scientific return from a single mission. We'd do exactly what Loeb is suggesting. 3i Atlas might be doing because it makes practical sense. It's efficient. It's logical. It's what any spacefaring civilization would likely do given the constraints of interstellar travel. So when we look at 3i Atlas approaching Jupiter, exhibiting behaviors that don't quite fit the comet model, arriving at this solar system from interstellar space at just the right trajectory to pass near the most massive planet we have, we're faced with a choice. We can assume it's all natural, all coincidence, all explicable through mechanisms we just haven't fully understood yet. Or we can acknowledge that it fits a pattern we'd expect if it were artificial, and that pattern deserves serious investigation rather than automatic dismissal. But let's ground this in specificity. Why Jupiter? Of all the places in our solar system, why would reconnaissance technology focus there? What makes Jupiter so strategically valuable that it would be worth the complexity of a deployment operation? Because if we can't answer that question, then the whole theory loses credibility. So we need to talk about what Jupiter actually is, what role it plays in our solar system, and why any intelligence studying our corner of space would inevitably focus significant attention on that particular giant planet, orbiting in the cold outer regions of our stellar neighbourhood. Jupiter isn't just another planet. It's a dominant force in our solar system, a cosmic anchor that shapes the orbits, evolution, and habitability of everything around it. When you look at our solar system as a whole, trying to understand how it formed, how it functions, and why Earth ended up being the kind of world where complex life could emerge, you inevitably come back to Jupiter. And if you were an intelligence from outside our solar system trying to understand what makes this stellar neighbourhood special, Jupiter would be the first thing you'd want to study after the Sun itself. Let's start with gravity. Jupiter contains more than twice the mass of all the other planets in our solar system combined. It's massive enough that it actually causes the Sun to wobble. When we detect exoplanets around distant stars, we often do it by detecting these wobbles. And if aliens were watching our Sun from dozens of light years away, they'd detect Jupiter the same way. That gravitational dominance means Jupiter's influence extends throughout the solar system. It affects asteroid orbits. It determines which comets get flung into the inner solar system and which ones get ejected entirely. It acts as a gravitational vacuum cleaner, capturing or deflecting objects that might otherwise impact the inner planets. This protective role is crucial for Earth's habitability. Without Jupiter, Earth would be hit by far more asteroids and comets. The rate of major impacts would be higher, potentially high enough that complex life might never have had the stable period it needed to evolve beyond simple organisms. We're not sure how much credit Jupiter deserves for making Earth habitable, but its influence is significant. If you wanted to understand why Earth developed life, you'd need to understand Jupiter's role in creating the conditions that allowed life to persist. Then there's the Moon system. Jupiter has nearly 80 known moons, ranging from tiny captured asteroids to world-sized bodies with complex geology. Europa, one of the 4 largest Galilean moons, is covered in ice, but believed to have a global subsurface ocean containing more water than all of Earth's oceans combined. That ocean is kept liquid by tidal heating from Jupiter's gravity, and where there's liquid water, where there's energy, where there's chemistry, there's the potential for life. We haven't found life on Europa yet, we haven't even confirmed the ocean directly, though the evidence is strong, but it's one of the top candidates in our solar system for hosting extraterrestrial organisms. Ganymede, the largest moon in our entire solar system, also appears to have a subsurface ocean. Callisto might have one too. These aren't dry, dead worlds. They're dynamic, complex environments where the conditions for life might exist beneath frozen surfaces. If you're surveying our solar system looking for places where life could emerge, Europa alone would justify extensive study. And all of these worlds exist in Jupiter's sphere of influence, heated by Jupiter's gravity, shaped by Jupiter's presence. Jupiter's magnetosphere is another factor worth considering. It's the largest structure in our solar system, extending millions of kilometers into space, far beyond the orbits of its major moons. This magnetic field traps charged particles, creating intense radiation belts that our spacecraft have to be specifically designed to survive. It also generates powerful radio emissions that we can detect from Earth with relatively simple equipment. These emissions are variable, affected by volcanic activity on Io, by solar wind conditions, and by other factors. If you're navigating through our solar system, Jupiter's radio signature is a beacon, a landmark you can use for positioning and timing. From a strategic intelligence perspective, positioning sensors near Jupiter makes enormous sense. You get proximity to potentially habitable moons that might be the most likely places for life beyond Earth. You get a gravitational vantage point that tells you about the dynamics of the entire solar system. You get a natural laboratory for studying magnetospheres, atmospheric dynamics, and planetary formation. And you get a position that's far enough from Earth that you're unlikely to be detected. Our telescope time focused on Jupiter is primarily for studying Jupiter itself, not for looking for artificial objects in Jupiter's vicinity. Let's think about this from a reconnaissance perspective. If you wanted to study our solar system without revealing your presence, where would you position your sensors? You wouldn't go to Earth, too risky, too likely to be detected. You wouldn't stay in the asteroid belt, it's spread out, chaotic, and doesn't give you a clear view of the inner planets. You wouldn't go to the outer solar system beyond Jupiter, too far away, too cold, communication lag becomes prohibitive. But Jupiter is the sweet spot. Close enough to observe the inner planets in detail, far enough away to remain undetected, located at a gravitational and navigational hub that makes it a natural focal point. Now consider what happened in our own history when we sent missions to Jupiter. Pioneer, Voyager, Galileo, Juno. We've sent multiple spacecraft specifically because Jupiter is scientifically valuable. We've invested billions in studying this planet because we recognize its importance. If we think Jupiter is worth studying, why wouldn't another civilization think the same thing? If our current level of technology leads us to send probes to Jupiter, why wouldn't a more advanced civilization do something similar, just at an interstellar scale? There's also the energy consideration. Jupiter radiates more energy than it receives from the Sun. It's still contracting from its formation, generating internal heat that drives atmospheric dynamics and provides energy that warms its moons. This internal energy source means Jupiter is more than just a cold gas giant, it's an active system with ongoing processes. For any technology that needs power, Jupiter's environment offers options: solar power from the Sun, energy from Jupiter's magnetosphere, even potentially harvesting hydrogen from Jupiter's atmosphere if you had the right technology. It's not just a waypoint, it's a resource-rich environment. The historical record also matters here. In 1994, Comet Shoemaker-Levy 9 impacted Jupiter in a series of spectacular collisions that astronomers around the world observed. The impacts created dark scars in Jupiter's atmosphere larger than Earth, demonstrating the kind of energies involved when objects hit Jupiter. That event showed us how Jupiter continues to interact with comets and asteroids, how it captures and destroys objects, how it shapes the population of debris in our solar system. If you wanted to understand impact risks for inner planets like Earth, studying Jupiter's interactions with comets would be essential. So when 3i Atlas approaches Jupiter, this interstellar visitor coming from outside our solar system, on a trajectory that brings it through the Jovian region, the question isn't really why would anyone care about Jupiter? The question is, how could anyone not care about Jupiter? If you're studying our solar system, Jupiter is where you go. If you're deploying reconnaissance assets, Jupiter is where you put them. If you're trying to understand what makes this stellar system potentially special, Jupiter is the key that unlocks that understanding. But here's where we need to balance speculation with skepticism. Because everything I just described about Jupiter's importance is true whether 3i Atlas is a natural comet or an artificial probe. The strategic value of Jupiter doesn't prove anything about 3i Atlas's nature. What it does is establish context. It explains why, if the deployment theory were true, Jupiter would be the logical location for that deployment. It makes the timing and positioning less coincidental and more comprehensible. And that brings us to a critical question. What do the skeptics say? What are the conventional explanations for everything we've observed about 3i Atlas? Because if we're going to take this investigation seriously, we can't just look at evidence that supports unusual theories. We need to examine the strongest arguments against those theories, understand where conventional science sees natural explanations, and honestly evaluate whether those explanations are adequate or whether they're being stretched to avoid uncomfortable conclusions. Science advances through skepticism. The greatest discoveries often came from people questioning accepted wisdom, but those discoveries were validated by skeptics who demanded rigorous evidence before accepting revolutionary claims. So when we talk about the possibility that 3i Atlas might be artificial, we have to engage seriously with the scientists who look at the same data and see nothing but a natural comet behaving oddly, but not impossibly. These aren't closed-minded dogmatists. They're careful researchers who know that extraordinary claims require extraordinary evidence and who believe the evidence for 3i Atlas being artificial simply isn't there yet. The standard explanation for 3i Atlas's brightness variations is outgassing. Comets are composed of various ices mixed with dust and rock. As they approach the sun and heat up, different volatiles sublimate at different temperatures. Water ice starts outgassing at certain distances from the sun. Carbon dioxide sublimates at greater distances where temperatures are colder. Other compounds have their own temperature thresholds. This creates a complex pattern of activity that doesn't always correlate simply with solar distance. A comet could have pockets of highly volatile materials that suddenly release, creating brightness flares. It could have rotation that periodically exposes more active regions to sunlight, creating periodic brightness variations. None of this requires anything artificial. Fragmentation is another conventional explanation for unusual behavior. Comets are fragile. They're held together by their own weak gravity and by the structural integrity of ice, which isn't particularly strong. As thermal stress builds up, as tidal forces from the sun or from planets stress the object, as internal pressure from outgassing exceeds structural strength, comets can break apart. When they fragment, they can suddenly brighten dramatically because you're exposing fresh, volatile interior material to sunlight. They can change their trajectory slightly because the act of breaking apart can impart momentum. This has been observed in many comets throughout history, and it's a perfectly natural process that needs no alien intervention to explain. The trajectory question has natural explanations too. Skeptics point out that interstellar objects enter our solar system from random directions. Some will inevitably pass near Jupiter simply by chance. Jupiter is a large planet with a large gravitational sphere of influence, and it sweeps out a significant volume of space. The fact that 3i Atlas's trajectory brought it near Jupiter isn't remarkable in fact. Any object passing through the inner solar system from certain approach angles would necessarily pass through the general region where Jupiter orbits. It's geometry, not intent. Regarding the spectral signatures that seemed unusual, skeptics argue that we simply don't have a large enough sample of interstellar comets to know what's normal for objects that formed around other stars. We've only confirmed a couple of interstellar visitors, and each one has shown us that interstellar objects can be different from solar system objects in various ways. Oumuamua had an unusual shape and acceleration. Borisov, another interstellar comet, showed different chemical signatures than typical solar system comets. This is exactly what we'd expect. Other stellar systems have different compositions, different formation histories, different evolutionary paths. An interstellar comet from a stellar system with different metallicity or different abundances of various elements would naturally have different spectral signatures than solar system comets. The scientific community also points to a methodological concern with jumping to artificial explanations. It's what's called the God of the Gaps fallacy, applied to aliens instead of deities. Throughout history, humans have attributed phenomena they didn't understand to supernatural or extraordinary causes, only to later discover mundane natural explanations. Thunder wasn't Zeus, it was atmospheric electricity. Disease wasn't demonic possession, it was microorganisms. Every time we've encountered something we didn't immediately understand, the natural explanation eventually emerged if we were patient and kept investigating. So the burden of proof is on those claiming something is artificial to demonstrate why natural explanations are insufficient, not just to point to gaps in current understanding. This is a powerful argument. Science has a strong track record of finding natural explanations for phenomena that initially seemed inexplicable. The history of astronomy specifically is filled with examples of objects or signals that seemed artificial upon first detection but turned out to be natural. Pulsars, when first detected, were briefly thought to possibly be artificial beacons because their signals were so regular. Quasars were mysterious for years before we understood they were distant galaxies with active supermassive black holes. Fast radio bursts seemed potentially artificial until we developed better models for magnetar activity. The pattern is clear: when in doubt, bet on natural. But here's where the skeptical position has its own vulnerabilities. While it's true that nature usually explains the unexplained eventually, there's a logical fallacy in assuming this will always be true. At some point, if technology from other civilizations exists and is present in our observational data, we will encounter something artificial. The question isn't whether we should be skeptical, we absolutely should be. The question is whether our skepticism is calibrated appropriately, or whether it's become a prior commitment that makes certain conclusions impossible to reach, regardless of evidence. Think about what it would take to convince the skeptical community that an object is artificial. You'd need to rule out all natural explanations, which is effectively impossible, because you can always propose new natural mechanisms we haven't considered. You'd need to detect clear signs of technology, but if that technology is designed not to be obvious, you might not detect those signs. You'd need reproducible observations, but interstellar objects pass through our solar system quickly, and we only get one chance to observe them before they're gone. The evidentiary bar is so high that it might be practically impossible to meet, even if artificial objects were regularly passing through our solar system. This is the core of Avi Loeb's critique of mainstream astronomical practice. He's not saying scientists are wrong to be skeptical. He's saying that skepticism has hardened into reflexive denial, that the null hypothesis has become natural unless absolutely proven otherwise beyond any conceivable doubt, which is a different standard than we apply to other astronomical questions. When we detect a new type of stellar object, we don't demand absolute proof that it's natural we observe it, develop models, refine those models, and accept the best explanation that fits the data. But when an object shows characteristics potentially consistent with technology, we demand ironclad proof before we'll even seriously consider the artificial hypothesis. The skeptics also face the challenge that their natural explanations for 3i Atlas, while individually plausible, collectively require a set of coincidences. The outgassing has to happen in unusual patterns. The rotation has to be just right to create the observed brightness variations. The trajectory has to happen to take it near Jupiter. The spectral signatures have to be unusual because of the object's origin, around a different star. Each of these explanations is reasonable, but when you need all of them to be true simultaneously to explain all the observations, you're building a model that's increasingly contrived. At some point, a simpler explanation, even if it invokes technology, becomes more parsimonious. This isn't to say the skeptics are wrong. They might be completely right. 3i Atlas might be a perfectly natural interstellar comet, doing perfectly natural comet things, and all the unusual behaviours might have mundane explanations that we'll understand better as we gather more data. But the skeptical position isn't proven either. It's a hypothesis, just like the artificial hypothesis is a hypothesis. Both should be tested against observations, both should make predictions that can be checked, and both should be refined or abandoned based on evidence. The reality is that we're in a period of uncertainty, which is uncomfortable but exciting. We don't know what 3i Atlas is. We don't have enough data to definitively say it's natural or artificial. We're watching it move through our solar system, gathering what observations we can with the limited time and resources available, and trying to make sense of patterns that don't quite fit our established models. This is science at its best, confronting the unknown, proposing competing hypotheses, arguing about evidence, and slowly working toward understanding. But to fully appreciate what's at stake in this debate, we need to zoom out from 3i Atlas specifically and look at the broader context of interstellar objects, the search for extraterrestrial intelligence, and humanity's evolving relationship with the question of whether we're alone. Because 3i Atlas isn't happening in isolation, it's happening at a unique moment in history when we're finally developing the technology to potentially detect evidence of other civilizations, when the scientific community is slowly becoming more open to technosignature research, and when the consequences of finding artificial objects in our solar system would ripple through every aspect of human civilization. We live in a remarkable time. For most of human history, questions about life beyond Earth were purely philosophical. the domain of speculation and imagination rather than empirical investigation. We wondered whether other worlds existed, whether they harboured life, whether intelligence had emerged elsewhere in the cosmos. But we had no way to actually find out. We could only guess, only dream, only hope or fear depending on our temperament. That's changed. In the span of just a few decades, we've transformed from a species that could barely see beyond our own atmosphere to one that can detect planets around distant stars, analyse their atmospheres, and search for biosignatures or technosignatures that would reveal life's presence. The detection of interstellar objects is part of this transformation. Until 2017, we had never confirmed the existence of an object from another stellar system passing through ours. We theorised that such objects must exist. Stellar systems should occasionally eject material that wanders through the galaxy, and some of that material should pass through our solar system randomly. But theory is different from observation. Actually detecting Oumuamua changed everything. It proved that we could spot interstellar visitors. It showed us that our telescopes and detection systems had reached the sensitivity needed to find these objects, even though they're relatively small and moving fast. And it raised the immediate question, now that we can detect them, what will we find? Oumuamua was strange enough on its own, with its unusual acceleration and its shape that seemed inconsistent with normal asteroids or comets. Then Borisov arrived, another interstellar visitor, and it looked more like a conventional comet, which was almost reassuring. It suggested that maybe Oumuamua was the outlier, and most interstellar objects would be recognizable, familiar, natural. But then came 3I Atlas, and here we are again confronting something that doesn't quite fit, something that raises questions, something that makes us wonder whether we're seeing patterns we don't want to acknowledge. Statistical models suggest that dozens or even hundreds of interstellar objects pass through our inner solar system every year. Most are too small or too faint to detect. Some pass through when our telescopes aren't looking in the right direction, but as our survey capabilities improve, we're going to find more of them. The Vera C. Rubin Observatory, when it comes fully online, will dramatically increase our ability to detect these objects. Future space telescopes will add to our capabilities. Within the next couple of decades, we'll have a much larger catalogue of interstellar visitors, and that catalogue will tell us something profound about the galaxy we inhabit. Will most of these objects be natural? Almost certainly. Rocks and ice ejected from distant stellar systems by gravitational interactions, wandering through space for millions of years, occasionally passing through our neighbourhood before continuing their journeys. That's what we expect. That's what the laws of physics and our understanding of stellar system dynamics predict. But if even a small fraction of interstellar objects are artificial probes sent by civilizations that mastered interstellar travel, reconnaissance assets surveying the galaxy, relay stations for communication networks, we can't imagine then everything changes. The question isn't whether technology exists elsewhere. The question becomes how much of what we're seeing is natural versus artificial, and how we distinguish between them. This is where technosignature science comes in. For decades, SETI focused primarily on radio signals, the idea that advanced civilizations might broadcast their presence, or that we might detect their communications leaking into space. That approach has value, and it continues through projects like Breakthrough Listen, which uses some of the world's most powerful radio telescopes to search for artificial signals from nearby stars. But technosignature science is broader than radio SETI. It includes looking for optical laser pulses, for unusual chemical signatures in exoplanet atmospheres that might indicate industrial processes, for megastructures like Dyson swarms that would alter the light curves of stars, and for artificial objects within our own solar system. The Galileo project, led by Avi Loeb, is specifically focused on this last category. The project aims to design and build instruments that can detect anomalous objects in near-Earth space, analyse their characteristics, and determine whether they might be artificial. This isn't about UFO conspiracy theories. This is about rigorous, systematic observation using scientific methodology to search for evidence of technology. If artificial objects are passing through our solar system, whether they're probes from other civilizations, artifacts left behind by previous visitors, or active reconnaissance assets, we need to be looking for them deliberately, rather than hoping to stumble across them accidentally. The concept of von Neumann probes is relevant here. A von Neumann probe is a hypothetical self-replicating spacecraft that could explore the galaxy more efficiently than sending individual probes to every star system. You send out a probe that reaches a stellar system, uses local resources to build copies of itself, and then those copies travel to other stellar systems and repeat the process. Over millions of years, even with relatively slow travel speeds, such probes could spread throughout the entire galaxy. If any civilization developed this technology and deployed it, the galaxy could be filled with probes right now, and our solar system could have been visited multiple times over its history. This sounds like science fiction, but it's actually serious scientific thinking about how spacefaring civilizations might operate. We're already conceptually close to building such technology ourselves. We have the physics, we have the basic engineering principles, we just need to solve practical challenges like power sources for interstellar travel and autonomous manufacturing systems that can work with asteroid materials. If we can imagine it with our current technology, a civilization even a few hundred years more advanced than us could potentially build it. So what would it mean if we confirmed that 3I Atlas, or any other interstellar object, was artificial? The implications would cascade through every domain of human thought. Scientifically, it would confirm that we're not alone, that intelligence has emerged elsewhere, that technology can persist across interstellar distances. Philosophically, it would challenge human exceptionalism, our sense of being the pinnacle of cosmic evolution. Culturally, it would force us to confront our place in a universe where we're newcomers rather than sole inhabitants. Politically, it might unite humanity around a common identity as a spacefaring species, or it might fracture us further as different groups respond differently to the revelation. But here's what's fascinating. The scientific community is increasingly open to these possibilities. A decade ago, suggesting that an astronomical object might be artificial was career suicide. Today there are serious research groups, funded projects, and peer-reviewed papers discussing how to search for technosignatures. The stigma is lifting, the taboo is weakening. Scientists are recognizing that the question of extraterrestrial intelligence is not only legitimate but essential, because if technology exists elsewhere and we're not looking for it, we're failing at our basic mission of understanding the universe. This shift in scientific culture is crucial context for understanding the 3I Atlas debate. Loeb isn't operating in isolation. He's part of a growing movement within astronomy that says we should take seriously the possibility that some of what we observe might be artificial. That doesn't mean assuming everything unusual is aliens. It means including artificial in the list of hypotheses we evaluate, testing it against evidence just like we test natural hypotheses, and following the data wherever it leads. We're also living through a broader moment of revelation about aerial phenomena that might not be conventional aircraft. Governments are releasing information about unidentified objects in our atmosphere that perform in ways that challenge our understanding of physics or of known technology. Whether these objects are advanced human technology, sensor artifacts, natural phenomena, or something else entirely, they're forcing serious people to ask questions that were previously dismissed as conspiracy theory territory. The overlap between this conversation and the conversation about interstellar objects isn't perfect, but there's a common thread. The recognition that we might be seeing things we don't understand, and that dismissing them automatically serves no one. The search for life beyond Earth has always been about more than just finding bacteria on Mars or detecting biosignatures in exoplanet atmospheres. It's been about understanding our cosmic context, about knowing whether intelligence is common or rare, about learning whether technology inevitably leads to self-destruction, or whether civilizations can persist for millions of years. These are profound questions, and 3I Atlas, regardless of whether it's natural or artificial, is part of how we explore them. Every interstellar object we detect teaches us something about the galaxy. Every unusual observation forces us to refine our theories. Every debate between conventional and unconventional explanations sharpens our thinking. But all of this broader context doesn't change the fundamental challenge we face with 3I Atlas specifically. We don't have enough data. We're trying to draw conclusions about an object millions of kilometers away that we can only observe indirectly through the light it reflects. We're dealing with measurements that have uncertainty, with observations that have gaps, with theories that make different predictions that are all consistent with current data. So before we can responsibly conclude anything definitive about whether 3I Atlas is natural or artificial, we need to confront honestly the limitations of what we know and what we can know, and that means talking about the evidence problem. Let's be blunt. We don't have proof that 3I Atlas is artificial. We don't have a photograph showing a spacecraft with visible solar panels and antenna. We don't have radio signals clearly originating from the object carrying messages in a structured language. We don't have spectroscopic data showing refined metals or synthetic materials that couldn't occur naturally. We don't have the kind of smoking gun evidence that would convince even hard skeptics that what we're looking at is technology rather than ice and rock. What we have is a collection of observations that don't perfectly fit the comet model, combined with a trajectory and timing that could be consistent with reconnaissance, interpreted through the lens of a hypothesis proposed by a credible scientist. That's interesting. That's worth investigating. But it's not proof. The challenge is partly about distance and scale. Jupiter is far away hundreds of millions of kilometers at its closest approach to Earth, much farther when it's on the opposite side of the Sun from us. At those distances, resolving fine details is extraordinarily difficult. Our best telescopes can see Jupiter itself clearly, can observe its atmospheric storms, can track its moons. But a small object near Jupiter, something the size of a spacecraft or even the size of a small asteroid, is at the edge of our detection capabilities. We can potentially detect its existence through reflected light, but actually seeing its shape, its structure, its surface features that requires resolution we simply don't have with current Earth-based telescopes. Our best space telescopes could see more, but you can't just point them wherever you want. They're booked years in advance. By the time you schedule an observation of a fast-moving object, it's already gone. Astronomical observation isn't like wildlife photography, where you can react instantly to what you see. It's slow, it's deliberate, it requires planning, and that makes studying transient objects incredibly frustrating. Then there's the sensitivity problem. Our instruments can detect very faint objects, but there are limits. If 3i Atlas deployed small probes that were designed to minimize reflectivity, perhaps coated with dark materials that absorb light rather than reflecting it, or shaped to minimize their cross-section, when viewed from certain angles, those probes could be effectively invisible to our current detection systems. We wouldn't see them not because they don't exist, but because they're below our detection threshold. Absence of detection isn't the same as detection of absence, a principle that applies throughout science, but especially in astronomy, where we're constantly pushing against the limits of what our instruments can perceive. Let's talk about what definitive evidence would actually look like. If we detected an electromagnetic signal coming from 3i Atlas, or from the region near Jupiter where objects might have been deployed, and if that signal had characteristics clearly indicating artificial origin structured patterns, modulation that doesn't occur naturally, frequencies that are suspiciously precise, that would be strong evidence. But detecting such signals requires that they're being transmitted, that they're strong enough to reach us, that they're at frequencies we're monitoring, and that we're listening at the right time. Miss any of those conditions and we'd detect nothing, even if the signals exist. If we could send a mission to 3i Atlas or to the Jupiter region to conduct close-up observations, we could gather definitive data. We could image the object from multiple angles, analyze its surface composition directly, detect any power sources or emissions at close range, potentially even observe deployed objects separating from the parent craft if timing allowed. But we can't do that. Space missions take years to plan and launch. By the time we could get a probe to where 3i Atlas was, it would be long gone, having passed through our solar system and continued into interstellar space. The window for direct investigation has already closed or is closing rapidly. This is the fundamental frustration of studying interstellar objects. They don't wait for us. They pass through. We get one chance to observe them with whatever instruments we happen to have pointed in the right direction at the right time, and then they're gone. It's like trying to study a rare animal that only appears in your region for a few weeks once per decade. You observe what you can with the tools you have, you take your best measurements, you form your best theories, and then you wait years or decades hoping another similar object appears, so you can test those theories with better observations. The burden of proof question is philosophically complex. In science, we generally assume natural explanations until artificial ones are proven, which is reasonable given that the vast majority of what we observe is natural. But this creates an asymmetry. Natural explanations are the default and only need to be plausible, while artificial explanations need to be definitively proven before they're accepted. That asymmetry made sense when we had no evidence that technology existed elsewhere in the universe, but now we know that planets are common, that habitable conditions likely exist on billions of worlds in our galaxy, that life emerged quickly on Earth suggesting it might be common elsewhere, and that intelligence and technology are at least possible outcomes of evolution. Given all that, is the default assumption still justified? Or should we treat artificial and natural as competing hypotheses that need to be evaluated on equal footing based on which better explains observations? There's also the problem of negative results. If we look for signs of technology around 3i Atlas and don't find any, what does that mean? Does it mean the object is natural? Or does it mean technology is present but we're not looking in the right way? Not at the right frequencies? Not with sufficient sensitivity? You can't prove a negative. You can't prove that something doesn't exist. You can only fail to find it, and that failure might be because it's not there or because you're not looking effectively. This makes the artificial hypothesis difficult to disprove, which is scientifically unsatisfying because good hypotheses should be falsifiable. Yet the natural hypothesis has the same problem in reverse. If we do eventually detect clear signs of technology, if better observations reveal structures that can't be natural, or if we detect signals that are unambiguously artificial, the natural hypothesis advocates can always claim that we're misinterpreting natural phenomena, that we need extraordinary evidence, that we should wait for alternative explanations to be fully explored. Both sides of this debate have ways to avoid falsification if they're committed to their position regardless of evidence. What we really need is more data, better data, and data from multiple sources. We need continued telescopic observation of 3i Atlas as long as it's detectable. We need to look for any objects that might have been deployed near Jupiter, searching systematically even though we're not sure exactly what we're looking for. We need to monitor radio frequencies and other parts of the electromagnetic spectrum for any signals originating from the region. We need to compare 3i Atlas to other interstellar objects we detect in the future, looking for patterns that might distinguish natural from artificial. And we need to remain open to both possibilities, natural or artificial, without premature conclusions in either direction. The upcoming observational opportunities matter. As 3i Atlas continues its trajectory, different telescopes will have opportunities to observe it from different angles, potentially revealing details we couldn't see in earlier observations. If its behavior continues to be anomalous, if new puzzles emerge that challenge natural explanations further, the case for investigating the artificial hypothesis becomes stronger. If natural explanations start fitting the data better as we gather more observations, then the artificial hypothesis becomes less compelling. This is how science progresses through accumulation of evidence, through refinement of theories, through honest evaluation of what explains observations most completely. We also need to think about what we'd do if we did confirm that 3i Atlas or any interstellar object was artificial. There would be immediate questions about communication, about intent, about whether these objects are active or dormant, about whether they're observing us or just passing through, about what information they might be gathering and transmitting back to wherever they came from. These aren't idle questions. These are practical matters that would require international coordination, scientific resources, and careful thought about how humanity responds to confirmation that we're being observed by technology we didn't create, but we're not there yet. Right now, we're in the evidence-gathering phase, the hypothesis-forming phase, the debate and discussion phase. We're watching, we're wondering, we're arguing about interpretations, and we're preparing for whatever comes next. And that's exactly where we should be curious, cautious, critical, and open. Because whether 3i Atlas is a comet or a probe, whether we're alone or observed, whether the universe is empty of intelligence or filled with civilizations we haven't noticed yet, the answer matters profoundly for who we are and who we might become. So what does all of this mean? Where does it leave us as we contemplate this interstellar visitor moving through our solar system, approaching Jupiter, exhibiting behaviors we struggle to explain? What should we take away from this investigation into one of the strangest objects in modern astronomy? And perhaps most importantly, what happens next, not just for 3i Atlas, but for humanity's evolving relationship with the cosmos, and with the possibility that we're not the only ones here? We started with a question that sounds like science fiction. Is an interstellar comet deploying alien probes around Jupiter? We've walked through the evidence, examined the theories, confronted the skepticism, and explored the implications. And if you're expecting me to give you a definitive answer to tell you with certainty whether 3i Atlas is natural or artificial, whether we're witnessing reconnaissance or just unusual comet behavior, I can't do that. Nobody can, not yet. But that's not a failure. That's exactly where good science lives, in the space between observation and understanding, in the tension between competing explanations, in the honest acknowledgement that we don't have all the answers yet. What we can say with certainty is that 3i Atlas doesn't fit neatly into our models. Natural explanations exist for its behaviour, but those explanations require stacking multiple unlikely factors, unusual composition, specific rotation, timely fragmentation, peculiar trajectory to account for all the observations. The artificial hypothesis, proposed by a scientist with impeccable credentials, offers a simpler framework that explains the patterns with fewer assumptions. Neither explanation is proven, neither is impossible, and that's the reality we have to sit with, uncomfortable as it might be, but discomfort is valuable. It means we're at the edge of our knowledge, pushing into territory we haven't mapped yet. Every major advancement in human understanding came from moments like this, moments when observations didn't match expectations, when conventional wisdom couldn't explain what people were seeing, when someone was brave enough or foolish enough to suggest that maybe our models were incomplete. Copernicus was uncomfortable, Galileo was uncomfortable, Einstein was uncomfortable, not because they were uncertain of their ideas, but because their ideas challenged everything their contemporaries believed. Avi Loeb is uncomfortable in precisely this way. He's challenging the reflexive assumption that everything we see in space must be natural, that technology from other civilizations couldn't possibly be present in our observations, that even considering artificial explanations is somehow unscientific. His challenge isn't radical, it's actually quite conservative, in the sense that it asks us to follow evidence wherever it leads rather than where we're comfortable going. And whether he's right about 3i Atlas specifically, he's definitely right about the broader principle. We need to be willing to see what's actually there, not just what we expect to see. This matters because we're entering an era where we'll detect more interstellar objects, where our surveys will become comprehensive enough that unusual visitors can't slip by unnoticed. We're building better telescopes, deploying more sensitive instruments, developing algorithms that can spot anomalies in real time. Within our lifetimes, we'll have a catalogue of interstellar objects large enough to draw statistical conclusions about what's typical and what's exceptional. And when we have that catalogue, when we can compare dozens or hundreds of these visitors, patterns will emerge. Maybe those patterns will confirm that they're all natural. Maybe those patterns will reveal that some are different in ways that natural processes can't explain. Either way, we'll learn something profound. The Jupiter connection will remain important regardless of what 3i Atlas turns out to be. If it's natural, then its trajectory near Jupiter still taught us about gravitational interactions, about how interstellar objects move through our solar system, about the observational signatures we should watch for in future visitors. If it's artificial, then Jupiter's strategic value for reconnaissance is now confirmed, and we know where to focus our attention when searching for technology. Jupiter isn't just another planet, it's a lens through which we can understand both our solar system's dynamics and how any external intelligence would logically approach studying us. What I want you to take from this isn't certainty about 3i Atlas's nature. What I want you to take is an appreciation for how scientific discovery actually works. It's messy, it's uncertain, it involves competing theories, incomplete data, passionate disagreements, and gradual accumulation of evidence that slowly tips the scales toward one explanation or another. The public often sees science as a collection of facts delivered by authorities who know the truth. But science is actually a process, a method, a way of thinking that prioritizes evidence over authority and conclusions over comfort. The question of whether we're alone in the universe is perhaps the most profound question humanity has ever asked. It touches philosophy, religion, identity, purpose, and meaning. For thousands of years we could only speculate. Now we can investigate. We can build instruments, gather data, test hypotheses, and slowly work toward an answer. That answer might be, yes, we're alone, which would be haunting and humbling, making us custodians of the only intelligence in a vast empty cosmos. Or it might be, no, we're not alone, which would be thrilling and terrifying, forcing us to reconceptualize our place in a universe where intelligence is common and where we're newcomers rather than sole inhabitants. 3i Atlas is one small piece of that investigation. One object moving through our solar system for a brief period, observed imperfectly with instruments that are powerful but limited. In 100 years, historians of science might look back on 3i Atlas as a turning point. the moment when humanity first seriously considered that interstellar objects might be technology, the first step toward a broader awakening about our cosmic context. Or they might look back and see it as a curious footnote, an object that seemed unusual but turned out to be natural, part of the learning curve as we figured out how to interpret interstellar visitors. Either way, this moment matters, this conversation matters. The fact that we're having this debate, that scientists are proposing artificial hypotheses and other scientists are demanding rigorous proof, that the public is engaged with questions about reconnaissance and technology, and the search for intelligence, all of that represents progress. We're not shutting down uncomfortable questions anymore. We're not ridiculing people who suggest possibilities outside the mainstream. We're doing what science is supposed to do, exploring, questioning, debating, and slowly building understanding through evidence and reason. So where do we go from here? We watch. We observe 3i Atlas as long as we can, gathering every bit of data possible before it passes out of range. We monitor the Jupiter region for any signs of deployed objects or unusual activity. We improve our detection systems so that when the next interstellar visitor arrives, we're better prepared to characterize it quickly and comprehensively. We continue the broader search for technosignatures, for radio signals, for optical beacons, for atmospheric signatures of industrial civilizations, for any evidence that we're not alone. We support scientists like Avi Loeb who are willing to ask hard questions even when it invites criticism. And we stay curious, stay critical, stay open to possibilities we haven't imagined yet. You're part of this. Every person who engages with these questions, who thinks critically about evidence, who resists the temptation to jump to conclusions while also resisting the temptation to dismiss uncomfortable possibilities, you're contributing to how humanity navigates this extraordinary time in our history. The future will judge us not by whether we were right about any specific object, but by whether we approach these questions with intellectual honesty, with openness to evidence, and with the courage to confront implications that challenge our comfortable assumptions. If you found value in this exploration, share it. Talk about it with friends, family, colleagues. These conversations need to happen not just in academic journals and scientific conferences, but in living rooms and coffee shops and comment sections. Democracy requires an informed citizenry, and when the question is as fundamental as whether we're alone in the universe, everyone deserves to be part of the conversation. Drop a comment and tell me, if you could ask the scientists studying 3i Atlas one question, what would it be? What aspect of this mystery matters most to you? And if we do eventually confirm that artificial objects are visiting our solar system, how do you think humanity should respond? These aren't academic questions, they're practical ones that we might need to answer sooner than we expect. Subscribe, because this story isn't over. 3i Atlas is still out there, still moving, still being observed. New data will emerge. New observations will either support the artificial hypothesis or undermine it. And beyond 3i Atlas, more interstellar objects will arrive, each one an opportunity to test our theories and refine our understanding. You'll want to be here for those updates, for those revelations, for whatever comes next in humanity's search for answers to the oldest question we've ever asked. We live in a universe of extraordinary scale and complexity, filled with billions of galaxies, each containing billions of stars, many with planets, some potentially harbouring life. We're one species on one planet, looking up at the cosmos and trying to understand our place in it. Objects like 3i Atlas remind us how little we know, how much we have yet to discover, and how the universe continues to surprise us no matter how much we learn. That's humbling, but it's also exhilarating, because it means the story is still being written, and we're the ones writing it. So stay curious, stay critical, stay open, and keep watching the skies, because up there, right now, things are happening that we don't fully understand, that challenge what we thought we knew, and that might just change everything about how we see ourselves and our place in this vast, ancient, mysterious universe we call home.